My name is Tassos with RF Elements, and today we'll be talking about really the most important antenna parameter for WISP networks, and that's beam efficiency. So, antennas have many so-called kind of textbook parameters, right? Being a WISP, you really need to know about all of them. No, not all of them, but in the WISP industry, there are only a few antenna parameters that you should really know and really care about. In general, it's fair to say that many of these antenna parameters are connected to one another, and sometimes they're connected in a very complex way. The textbook parameters, that are usually understood to express the ability of an antenna to deal with interference are like front to back ratio, or side lobe levels, or even the ETSI masks that you sometimes see. These are ones you probably know, or at least you've probably heard about them at least, right? So, the one we at RF Elements believe is really the most important in terms of noise suppression is beam efficiency. So beam efficiency is the ratio of energy contained in the main lobe to the total energy an antenna radiates. So in other words, it tells us what part of the radiated energy is going into the main lobe. The higher the beam efficiency is, the more energy the main lobe delivers, right? So in other words, this is where you want the energy to be, and less everywhere else. So since side lobes do a lot of harm in the unlicensed wireless world, the beam efficiency of an antenna you use is sometimes is something that is really worth knowing about. So not only is it worth knowing about, but it should be a decision factor when you're thinking about how to deal with interference issues that you might be having. So to give you a practical example, here you see the radiation pattern of a generic parabolic dish antenna. It has a beam efficiency of about 40%. So this means that 40% of the power the antenna radiates goes into the main lobe. So, what happens to the remaining 60%? So that remaining energy goes everywhere else. And since everything outside the main lobe, since everything is outside the main lobe, it's really a side lobe. And really, it gets into these side lobes and creates a lot of noise and a lot of waste. So you should note here that the side lobes are highlighted here. So beam efficiency includes all of the side lobes of the antenna, not just the first lobe or maybe the second lobe. So it's really anything other than the main lobe is considered a side lobe. So, if you want to compare, two antennas in terms of side lobe performance, beam efficiency makes it extremely simple. The higher the number is, the better, right? So, like in this example, we use our ultra horn, which has a beam efficiency of 99%. So only 1% of the power, it radiates are in the side lobes. A generic dish antenna has a beam efficiency of about 40%. So the remaining 60% of the energy it radiates, again, is in the side lobes. So 99% is clearly more than 40%. Therefore, the ultra horn is a better antenna in terms of noise suppression. It's probably one of the best in the market today as far as beam efficiency goes. So let's also look at some of the parameters you might already know, like front to back ratio. Front to back ratio is one of the many manufacturers include in their antenna, in their antenna data sheets, and we'll have a small recap of what front to back ratio is. So the conventional thinking about front to back ratio is that if it's high, it means an antenna is a good choice for co-location. So if the antennas are back to back and both have a high front to back ratio, they will not interfere with each other. This is really wrong, right? So the reality is that front to back ratio does not mean that that antennas are good for dense co-location in every possible setting, right? So it's simply a misconception, right? It's important to understand that, because the next time you have a conversation about front to back ratio, you could be sure that if anybody says that high front to back ratio means an antenna is great for colocation, you'll know that the person is either misinformed or simply didn't really go deep enough into the topic, and we'll kind of discuss some of that. So, high front to back ratio means that the back lobe is small, right? So this is the lobe, pointing in the opposite direction of the main lobe. It could also mean that a group of side lobes around the back lobe is small, depending on the definition or the way front to back ratio is actually determined, right? So, front to back ratio is easy to understand looking at a radiation, pattern of an antenna. And in this example, we show the radiating pattern of a directional patch array antenna. So the front to back ratio is the difference between the gain of the main lobe and the gain of the back lobe, which is pointing backwards. In practice, front to back is, often determined based on the strongest side lobe from a plus or minus 30-degree angle around the back lobe because of possible manufacturing, assembly, or material imperfections. So because of these imperfections, the back lobe, might not be just a single lobe, but it can be divided into several minor lobes around it. So it's not just a single point, or it's not always a single point. So nevertheless, back lobes are, one of the many side lobes antennas have in the WISP industry. So if a back lobe is one out of many side lobes, then it's probably not so important, right? This is a typical error in the interpretation of front to back ratio, and it doesn't say anything about the other side lobes that are there. So when you have two antennas that are exactly back to back, which is really a rare scenario, high front to back ratio can help to decrease the interference level that radios will see. But like I said before, typical antennas used in WISP networks have plenty of side lobes, and the back lobe itself, can be quite complex, right? So as soon as there are, more links on the tower, or the co-located, antennas are not exactly back to back, you are looking at, potential issues caused because of, all these other side lobes that are there. So high front to back ratio really, provides no protection in high noise environments. So, for urban and suburban areas with other wireless links in the neighborhood, or even on the same tower, front to back ratio is kind of irrelevant, right? These other links may be yours, or they could be your competitors. Either way, they're probably using similar hardware to you, meaning that their antennas, most likely have just as many side lobes that create noise, and it's received through the rest of the side lobe. So it's not just about that simple back lobe of an antenna that tells you how well it isolates and how well it co-locates with other radios and other antennas, whether they're yours or potentially a competitor's, right? So another antenna parameter that we'll talk about here is side lobe level, right? So in real life, it is similar to front to back ratio. So let's have a little deeper look into the details of that. So side lobe level is the difference between the gain of the strongest lobe, right, and the main lobe. So the strongest side lobe and the main lobe. So it's more useful than front to back ratio because it at least points out the strongest side lobe. If the side lobe level is high, the strongest side lobe is close to having the gain of the main lobe, which makes it a very poor antenna for a WISP network. So the issue with side lobe level is that it does not talk about all the side lobes again, right? So it's just a generic, all-encompassing term for the side lobes themselves. So side lobe level is defined by the strongest side lobe, right? Which again is only one side lobe out of many and defined at a single frequency. And this is really important, right? Since side lobes are changing with frequency, the noise level also changes with them. So despite knowing, what the strongest side lobe is at a single frequency, it's not very useful in the bigger picture, since simply switching the channel changes everything about the antenna, right? So, side lobe level is therefore a similar metric to front to back ratio. It tells you what the strongest side lobe is at one frequency, but nothing about the rest of the side lobes throughout the entire useful bandwidth of an antenna. And that's the biggest issue with these metrics. In WISP networks, all side lobes matter, not just a single side lobe. So to kind of sum it up, right, not all antenna parameters are practically useful for WISP networks, right? So it simply depends on the context an antenna is used in, right? In the end, it is up to the user to mainly the manufacturers to responsibly look at each of these antenna parameters and evaluate whether it is useful, in this framework of the WISP networks or the WISP industry or not, right? So the conclusion for front to back ratio and side lobe levels clearly says that, these two are really not so important because they tell you a very limited part of the story about the side lobes of an antenna. And, if you're wondering why WISP antenna manufacturers use them, it's probably a guess, but it would, probably it's the, the remnants of a time when, these particular parameters were, kind of the only easy ones that were easy to determine without enough, computational power that we have today, right? So in order to calculate, front to back ratio or side lobe level is quite simple. But today, we have much more powerful computers, much more powerful simulators, much more precise measuring instruments that, we're able to measure side lobes, and we're able to do things at a much higher level today that really what you're looking at in spec sheets are kind of, the old days of, how things were done based on their limitations of what they can calculate. And for antenna parameters. So, ETSI masks are something else that, you might know, and you might have seen some antenna manufacturers kind of quote or put in their spec sheet. So, the ETSI masks, to a degree also serves as a parameter that says how well an antenna performs in terms of noise, right? So, it's important to clarify that, ETSI masks consider two principal cuts of an antenna radiation pattern, just the azimuth cut and the elevation cut. So, these masks consider two slices of a completely three-dimensional radiation, pattern. So again, it's rather an incomplete measure from the point of view of the whole radiation pattern and all of the side lobes that matter in a WISP network. So again, even though the ETSI masks are becoming more and more common, it's still just a small portion of the overall radiation pattern that antennas put out, and therefore only giving you a limited slice of the information that's useful to you. So, ETSI masks are, observed at, usually three frequency points: the beginning, the middle, and the end of the spectrum in which an antenna works. So nonetheless, the rest of the spectrum, which is rather wide in the case of a WISP network, is not included in the ETSI definition or in the ETSI mask. Again, it's giving you a little bit more information. It's, part in the beginning, part in the middle, and part in the end of the frequency range of an antenna, but it's leaving out everything in between. So, so how does one, get to the ETSI mask or, what does it really look like, right? So first, you start with the polar plot that you know from data sheets, right? And then basically, if we redraw that on an XY plot, the ETSI mask is this blue dashed line, right, which says that the radiation pattern should stay below the mask so that the antenna can be declared compliant within that given ETSI norm, right? So, the mask, does change with angle, so it really has a few steps visible from this plot. If the radiation pattern doesn't stay within the mask, the antenna is not compliant with the standard, which is the case, for this particular example, where you can see towards the edges, you can see that the beam pattern goes outside of the mask and therefore is not compliant with one of the many ETSI mask standards that are out there. So, the masks are, somewhat easy to understand, and, to their credit, they consider at least the whole 360-degree circle of the radiation pattern, but unfortunately, only 2 cuts of the 3-dimensional radiation pattern at only 3 frequency points of the whole spectrum of an antenna works within. The vast majority of the usable spectrum is not included within this mask, right? So, in terms of interference suppression, it's really, again, not very useful and not complete information. So whenever you see an antenna being compliant with an ETSI standard, know that it, does not bring much added value in terms of suppressing noise in a WISP network, because again, it's not giving you the whole picture throughout the entire operating frequency of the frequency range of a particular antenna. So, at RF Elements, we strongly believe in doing the right thing for our customers and the WISP industry, right? So we did more research on this, and we found out about a parameter called beam efficiency, which really is the most complete measure of side lobes out there. And when I say the most complete, I'm not just saying kind of trying to throw out some marketing fluff. Really, the following slides will kind of explain to you why, and hopefully give you a better understanding of why beam efficiency is really a much better parameter to judge an antenna's noise immunity. So, beam efficiency is the parameter WISPs really should be looking for, and other manufacturers should be using or should have used, right? So it really gives the right answer to the question about side lobes. So despite you might have never heard about beam efficiency before, RF Elements does what we believe is the best for our customers, even if it means bringing in something never considered before, and which might be different from what other manufacturers say, right? So if beam efficiency is a ratio of the energy contained in the main lobe to the total energy an antenna radiates, it is also a measure of side lobes. So we can get the percentage of the side lobes by subtracting beam efficiency from 100%. It's quite easy to see what beam efficiency is and how important it is. So we can get the beam efficiency of an antenna by measurements done like in an RF isolation chamber, right? Using measuring instruments. So it's kind of like what you see here in this image. The antenna is attached to like a rotary stage which rotates in 2 axes and then can measure the radiation pattern of that antenna. So based on the measured radiation pattern, we can calculate beam efficiency. So, if the model of an antenna is really precise enough, or an antenna pattern is simple, right, we can also simulate or use simulation software to do the same thing. So, basically, obtain the radiation pattern, and based on that, we can calculate beam efficiency. So again, some simple beam shapes allow you to simulate beam efficiency and get them without having to measure them. So it makes it a little bit easier. So if an antenna's beam efficiency is 40%, again, then 40% of the power the antenna radiates, goes into the main lobe, and the remaining 60%, therefore, must be in the side lobes. So, note that all the side lobes are highlighted here. So, beam efficiency includes, again, all of the side lobes of an antenna, not just one, or it's not just a slice of the radiation pattern, right? But the whole package in full 3D. So similarly with sector antennas, if the beam efficiency is, let's say, 58%, the rest of the energy, the 42%, is going out through all of the side lobes. So, WISPs use a really wide chunk of spectrum, and I should probably be a little bit more specific because we're talking about 5 gigahertz here, where we have almost we have an entire 1 gig of spectrum to use, right? So, so even though WISPs use a wide chunk of spectrum, in antenna textbooks, beam efficiency is also defined at a single frequency and for a single polarization. So, this is the case for most, parameters that you find in textbooks, right? And again, it is up to the user and mainly the manufacturer to consider whether one should care about the whole bandwidth or just a single frequency point. Since, again, as I mentioned earlier, the computational power is much more affordable these days, than it's been in the past. The choice between wideband or narrowband information is really a matter of deciding, what's important rather than, trying to figure out what we can do. So luckily, again, today we can easily do both, right? So in the WISP industry, it makes perfect sense to average the beam efficiency over the bandwidth of an antenna because, WISPs use, again, antennas in a wide frequency range. So it only makes sense that an antenna should perform well in that whole bandwidth and not just, again, in a single or a couple of, frequency points in the operating frequency of that antenna. So therefore, if we extended, at RF Elements, we extended that textbook definition of beam efficiency to a number that is the average of beam efficiency over the whole useful bandwidth of our antennas and over both polarizations, right? So this really turns the kind of textbook definition into a sort of super parameter, right? So with these previous parameters we talked about, front to back ratio, ETC masks, and side lobe levels, where they looked at a particular parameter at one frequency or maybe at a couple of frequencies, we're able to look at it in both polarizations across the entire spectrum and therefore average it out. So it really becomes a super parameter because it has really a lot more information and it's a lot more meaningful. So, it really is a much more robust and more reliable measure of side lobe performance than a single frequency, again, a single polarization or anything else that's really out there these days. So, the vast majority of antennas used for, sectorial coverage in WISP networks are either patch array antennas or horns, right? So, the patch array have, many frequency dependent side lobes, right? So their beam efficiency are usually around 60%, depending on the manufacturer and the design quality of that antenna. RF Elements horns, both symmetrical and the asymmetrical kind, have a beam efficiency between 90 and 95%. So in this graph, you can see other horns there, right? But this is really to highlight that it takes a considerable effort to design a horn antenna such that its beam efficiency is high, right? The stable and zero side lobe performance is not a given because it's a horn. We put a lot of effort into our antennas to have the beam efficiency at 90+ percent, right? So, don't be fooled by, why our antennas perform so well is because they're a horn in general. It's because of the considerable effort we put into it to make sure that it has a high beam efficiency and all these other parameters are well performing as well. So, similarly with point-to-point antennas, patch arrays, are again really at the bottom of beam efficiency. Sorry, this is not playing here. Sorry, I apologize. So really, again, patch arrays are at the bottom of beam efficiency, due to the many dependent side lobes, collecting and transmitting noise and really hurting WISP networks. So dish antennas are somewhat better, and generally, the bigger the dish, the better the beam efficiency becomes. If the antenna is carefully designed and well manufactured. So with any antenna, though, the compromises that are accepted at the design stage really can't be compensated for by manufacturing quality. So a well-manufactured antenna doesn't mean that it's going to be a great performing antenna if the manufacturer, compromised on some of the parameters in the design stage. So, what is really interesting here, though, is that the ultra horn has a beam efficiency of 99%. So, over the whole bandwidth of operation and in both polarities, the beam efficiency of the ultra horn is practically perfect. Only 1% of the RF signal, is in the side lobes, right? So if you ever wondered, is ultra horn worth the extra money compared to a dish? This may be a very clear answer with a 99% beam efficiency. It's probably the best performing antenna in the market in terms of noise suppression and at the gain it has, right? So I don't want people to think, which often is misunderstood, and they expect a 24 dBi ultra horn to outperform 30 dBi dishes or something like this, which have a lot more gain. So again, at the gain level, a 99% beam efficiency is extremely, extremely impressive. So again, beam efficiency, sorry. 1 second, I apologize. My slides. Here we go, sorry. Okay, so beam efficiency tells you everything about side lobe performance. Again, the higher it is, the better the antenna performs, right? So, forget front to back ratio, forget, side lobe levels or even ETSI masks, and focus on the beam efficiency of an antenna when you have to deal with noise, right? So not only is this the most, complete measure of side lobes, but it's also extremely robust measurements of side lobes, because again, it's, averaging over frequency in both polarities. So a lot more data has been collected to give you the beam efficiency number. So therefore you get a much better picture of what it's like. So, since it rarely happens that a wireless link is, situated in a completely isolated place, the interference, is present almost everywhere, right? So we know that some areas are less noisy than others, but really noise is everywhere, no matter how isolated you are, whether it's from home routers and other things that are in your operating area. So really the noisier environment, the more important beam efficiency is of an antenna, because again, the higher the beam efficiency, the better the noise isolation. So, recently you may have heard claims of other antenna manufacturers saying, for example, that this sector patch array antenna works like a horn in terms of avoiding noise or something similar. Really, these claims, I would ask a question. Well, what's the average beam efficiency of that antenna? If the beam efficiency of is of a similar value, then I would agree. But otherwise, if beam efficiency is something below 90%, you can be sure that there's nowhere near the same performance of a horn. So, in this, kind of following section, I'll tell you a little bit more about the practical consequences of using an antenna with high and low beam efficiency. So we can kind of, sum up that, the effect of high beam efficiency, into really one statement. Higher beam efficiency equals higher throughput because you have better signal. So, in a sector with, let's say no other links in the area, you may not mind so much if they have some side lobes, right? But as soon as the number of sectors grow, their side lobes cause, you know, the noise floor to rise, right? So higher noise floor equals lower throughputs, you know, and the beam efficiency of patch array sectors is, you know, something on the order of roughly 60%. So, you know, the remaining 40% of the energy, again, are in side lobes that collect and transmit interference, you know, to other links within yours or even your competitors' networks, right? So again, low beam efficiency equals lower throughput and consequently, you know, more unsatisfied customers. So, you know, low beam efficiency of dish antennas work in a very similar way, right? You know, the side lobes, you know, collect noise from its surrounding areas and transmit it, you know, to, you know, all other neighboring links. So whether it's a backhaul link or a distant narrow sector, you know, the beam efficiency of around 45% means, again, lower throughput in a higher noise area. You know, replacing, you know, just a single low beam efficiency patch array sector with a high beam efficiency horn antenna, you know, the low noise level in urban or high density areas is, you know, effectively avoided because high beam efficiency means no side lobes, and no side lobes means no interference or low interference. And the final effect is higher throughput. So, you know, addressing the most pressing problems of, you know, the WISP network really becomes a much more straightforward, and really the, you know, the only advice to share here is, again, use antennas with high beam efficiency. Again, high beam efficiency, it translates into higher throughputs and therefore better service to your customers. So, you know, radio manufacturers are also trying to help with noise with things like GPS synchronization, which, you know, tries to ensure that the radios, you know, in your network transmit and receive at the same time. And, you know, it's to protect you from basically self-interference, but, you know, not from side lobes from competitors' antennas in your area, right? So again, a high beam efficiency antenna ensures that you really don't have to worry about the interference from most of the competing WISP because it does not receive the noise. So you really don't need to try and deal with it in the first place, right? So the absence of the side lobes and having a high beam efficiency antenna means you hear less noise. Therefore, it's easier to coexist in these noisier areas, and therefore you have a better user experience and hopefully higher throughput. So, you know, beam efficiency is a very practical antenna parameter, right? So where before the discussion was about side lobes and, you know, it was limited to, you know, many side lobes versus little, or yes versus no, you know, beam efficiency, you know, is a number from 0 to 100%, and it's easy to compare side lobe level performance between an antenna, between different antennas. So now that you know front to back ratio or side lobe levels are parameters that are, you know, I don't want to say not important, but less important and less useful in the WISP industry because, you know, they only consider one side lobe out of many, you know, an antenna might have. You know, beam efficiency includes all of the side lobes, which makes it a very useful metric. Including all the side lobes removes, you know, any of the ambiguity and you know, you can be sure that, you know, this metric is really more reliable. So always ask whether, you know, a parameter is single frequency or wideband in the WISP industry, right? So when you're looking at a performance parameter of an antenna, you know, you should ask the manufacturer in which you're buying it from, you know, is that parameter again at a single frequency, or, you know, is it a wideband, you know, parameter, right? Because this really is a must, you know, because again, you know, the spectrum is shared by many, so therefore, you know, wideband performance is vital to your success. You know, RF elements addition to, the beam efficiency definition to average it out over both polarities and the entire antenna bandwidth, you really can't do better than that, right? So you don't really have to ask, because our parameters are given, again, across the entire spectrum and taking into consideration, the entire radiation pattern of an antenna. So, it really, to make it kind of easier for users, we have added beam efficiency to our antennas, and it's in all of our data sheets now. So we are a very transparent manufacturer, and we really want to provide our customers with the information that's really important to them. So, user education is really another important part of our awareness activities and things that we do. So, it's one of our many kind of first in the WISP industry things that we at RF Elements really can put on display here, right? So, our idea is that only educated customers can make qualified decisions, right? So we are also very open about myth busting and doing things like that, because there are many myths out there and misconceptions that really create a big problem for many users in our industry. And a lot of the stuff that we know or we think we know are kind of remnants of things from a long time ago. And really, when it comes to antenna performance, the requirements and the parameters that are important of an antenna are different today, because the radios are much more complex with higher modulation rates and a lot of higher functions that are available, that the parameters that we paid attention to 10 years ago are not as relevant today as they were back then. So I think it's important to educate the industry and to point out what's important today and change the information that's delivered. So it's a really big part of what we do at RF Elements. So I ask everybody to kind of join our online community, right? We have a forum, rfelab.com, where you can share ideas and talk to us and get a lot of information. And then, of course, on social media, right? Facebook, Instagram, Twitter. Facebook is probably one of the most widely used social media platforms in the WISP industry. And there's a lot of information there, a lot of WISP sharing their stories and how they do things. So you could definitely find us there and join us there. I'd like to say that in our webinars we use third-party trademarks, and they're solely to state the compatibility with our products. So all rights of trademark owners are reserved. And for more details, please check the product disclaimer on our website. And with that, we'll open it up to Q&A. Hopefully people will have questions. I love questions, and I will answer anything that's asked.
Perfect, thanks, Tassos. We do actually have some questions, so that's awesome. So the first question I have is, the beam efficiency parameter also applicable for the RX of the antenna?
Can you say that one more time?
Yes. Is the beam efficiency parameter also applicable for the RX of the antenna?
For the RF, that's exactly what it is, right? So the beam efficiency is just the simplest way of saying is it's the percentage of energy that the antenna radiates and how much of that energy is in the main lobe. So yes.
All right, perfect. Okay, so another question, possibly shifting gears a little bit. Are you able to quickly talk about the new AS-520 and how that differs from horns, but its new design and how efficient it could be?
Yeah, absolutely. So again, the new array sector that we have, which is basically a updated redesign of our previous carrier class sector, is a patch array sector. So it's like, I don't want to say it's like all the other patch arrays out there, but it is in the sense that it has side lobes, right? And its beam efficiency falls within the kind of range that you see typically for other patch array antennas out there. Now, we've done a lot with the integrated back shield, which help to alleviate a lot of the parasitic side lobes that are created with the traces that feed all the patches that create the beam for you. So our beam efficiency is higher than some other sectors out there, but it's again, it's nothing like a horn. Again, the efficiency is nowhere near as high as our horn specifically. Again, because it's a patch array. So, we say this often in our webinars and in public all the time. You can't escape the kind of design of particular antenna models. So patch array sectors have side lobes. If manufacturers tell you they have no side lobes, they're more than likely lying to you, right? You just can't get away from it. The same thing with dish antennas. Dish antennas and our dish antennas, the ultra dish line, have side lobes, right? So, antenna manufacturers can tell you that, yeah, you put this shield kit on it and you have no side lobes, or we'll create a deep dish versus another type of design. None of these things eliminate side lobes. They can suppress them, like we've tried to do with our patch array with the back shield, like we try to do with our particular design of parabolic dish to reduce the amount of side lobes, but they are always there.
Perfect. Next question I have, are there any plans for CBRS antennas?
Absolutely. So that's actually in the pipe right now. I can't really speak to, I know everybody wants to know if it's going to be a horn or not. Chances are you'll probably see a really nicely designed patch array sector for CBRS to start, but it's definitely in the pipe, yes.
Great, thanks. The next question I have is, do you have any adapters for Ubiquiti Rocket Prism 5AC Gen 2 with GPS antenna and also LTE Rocket?
Yes, absolutely. And actually, it's the same adapter. So if you go on our website and you go under adapters, you'll find the TPA PAF. That's PAF, and it stands for Prism Air Fiber. So it's a single twist port adapter that works with both all of the Prisms, Gen 1 and Gen 2. Again, only 5 gigahertz, and all of the air fiber. So the air fiber 5X, the 5X HD, and the LTU as well. And it has a convenient storage place for the GPS puck in the adapter itself. So a lot of people don't always know this. Some people thought that the GPS was built into the adapter. It's not. You have to take the GPS puck that comes with the radio that you buy from Ubiquiti and you insert it and mount it inside the adapter. So that's the TPA PAF, PAF.
Awesome. I don't see any other questions coming through, so I think it would be safe to wrap it up.
Okay.
If there are any other questions that do arise, please reach out to Tassos at RF Elements and Streetwave. We're here to help. Tassos, thank you so much for presenting today. This is very useful information. Thank you for all the attendees that attended. If you wanted to just say a few more last things before we go, please do so, Tassos.
Yeah, I'll just say, as we always say in our last slide, stay tuned, right? We're not done yet. We have a lot more to offer the industry, a lot more exciting products coming out. We've done a lot in 5 gig. Now it's time to move into other frequency bands. So stay tuned. A lot of exciting stuff coming. And thanks for taking the time to listen to this webinar today. Thank you.
Thank you, everyone. Have a good day.
Bye.